I'm going to go ahead and share the PowerPoint for our next lesson here. Okay, so I just want to begin with a few announcements. The first announcement is obviously I'm putting these PowerPoints up later than usual. I usually put them up on Monday, and you guys have until Friday to complete them, but because of the holiday weekend, I'm going to be uploading these on Tuesday, and you will have until Sunday to complete them. They are going to be broken down again by activities. These are going to be pretty long videos, and I'm going to have you guys watch a lot of YouTube videos on your own. There's a lot of concepts in this week's exercises, and it's just kind of one of those things that's easier to see in 3D than just on a PowerPoint. So I'm going to refer you to a lot of YouTube videos. I'm going to probably not explain things as thoroughly in the PowerPoint and just let you go ahead and watch those videos so you have you don't have to hear everything twice. The other announcement I want to make was that I will be accepting late assignments moving forward. There will be a deduction, obviously some type of penalty for turning it in late, but I will be accepting them late. So please, if you could put those on Canvas, great. But if you can't because it locks you out, I have to kind of play with Canvas and see if how I can allow that. If it locks you out, just go ahead and email it to me, and I'll just manually change your grade in the Canvas site. And that's about it. Okay, so let's go ahead and get started. So the main concept is going to be looking at the biological molecules that we come across constantly in biology, and those would consist of carbohydrates, proteins, lipids, and nucleic acids. All of these macromolecules are composed of essentially like multiple monomers. So it's just like the same thing over and over again, just connected in a certain arrangement. So although the structures look kind of daunting and the concepts are daunting, it really comes back just to this one simple structure just growing. So in order to kind of attack those macromolecules, we have to understand chemical bonding at a very basic level. So we're going to go ahead and review chemical bonding. I know it may have been a while since some of you guys learned these concepts, so I do kind of take it slow, and I do give you guys a lot of resources, and I am expecting you to watch all the videos that I have put throughout this PowerPoint. So first we just need to learn about atoms. So atoms, each element consists of one kind of atom. Atoms are composed of, sorry, let me go ahead and change this before I go any further. So here we have a helium atom. It is composed of, in the nucleus, we have protons, which are represented in green, and those are positively charged. And we have neutrons, which are represented in brown, and those are neutral. So our nucleus consists of protons and neutrons. In our surrounding the nucleus, you will find electrons. So here it is shown in an electron cloud, and you see two electrons that are negatively charged. So this is actually how we think of atoms. We think of them in these electron clouds. But when we're learning about them, we tend to think of them in orbits or shells. It's just easier to comprehend when we visualize them like that, but in all actuality, they're actually in these clouds, because they're not constantly moving at a predetermined speed or trajectory like we think of planets in the solar system. So it's actually pretty random and I guess chaotic. So it's more of a cloud than an orbit. And then, yeah, we'll leave it at that for now. So these atoms can transfer or share their unpaired electrons to form these chemical bonds. And that's how these atoms will grow eventually into molecules, is by forming these bonds. So these bonds hold atoms together to form molecules. So why do we need to learn chemistry in a general bio class? Well, if you take any biological system apart, you will eventually end up at a chemical level. So we're going to begin by reviewing atoms, which atoms are building blocks of molecules, like I just said, and they make up all living and non-living things. So once again, the makeup of the atom: in the center, what we call our nucleus, you have positively charged protons, represented here in blue, and neutral neutrons, which are represented in this like orange-red color. And then surrounding your nucleus, you have these electron shells, and that is where your electrons are. So here we have 6 protons, 6 neutrons, and 6 electrons. So like I said, your electrons will orbit your nucleus, and you have your inner shell, which can hold up to 2 electrons, and then you have your outer shells, which can hold up to 8 electrons. And then if this outer shell, the second one, had 8 electrons, then you would get a third outer shell if you had a leftover one. If not, you would just be satisfied with your second outer shell. But this up here is just showing how you have your nucleus in the center, which is that tiny little thing, and then it shows your electron cloud. And like I said, they don't actually go in this nice little orbit like we think of. It's pretty chaotic and disorganized, and yeah. And another thing is your electron shell closest to your nucleus is considered a low energy electrons, and your outer shells are high energy. So if you think of it, your electrons here, they can only move so much. They have so much space to like move around and create this disorder, whereas your outer shells have more space to be moving around and create disorder. So these are your high energy out here. So okay, let me go to the next slide because this is easier to see. So if we were to go to our periodic table and look up carbon, we would see this here. We would see something like this. It's sometimes just represented a little bit differently depending on the periodic table you're using. But essentially, we would see that the atomic number for carbon is 6. Your atomic number is going to equal your protons. So carbon has 6 protons, which is shown here, 6 protons. When the carbon is neutral, you will also have 6 electrons. The way we determine our neutrons is essentially you take the weight, or your protons plus your neutrons will equal your atomic weight. So carbon 12, this is carbon 12 here, will have 6 protons and 6 neutrons. So we have 6 protons, 6 neutrons in our nucleus, and then we have 6 electrons. You can have a different number of neutrons depending on the isotopes. So as you can see, we have carbon 12, but it also has different isotopes. We have carbon 13 and carbon 14. In carbon 13, you have 6 protons with 7 neutrons, which will give you the atomic weight of 13. And in carbon 14, you have 6 protons and 8 neutrons, which will give you the carbon weight of 14. So this essentially will change the number of neutrons you have, and it's going to affect the molecular weight or the atomic mass. And in biology, structure will always dictate function. So this will give carbon different properties. So atoms can have an unequal number of protons and electrons. So like I said up here, in a neutral state, your protons and electrons will be equal. So this is a neutral state. But if one outweighs the other, then you have an ion. So if you were to have more protons than electrons, you would have more positives than negatives. So you would have what is called a cation, and an example of this is calcium. If you had more electrons than protons, so you have more negatives than positives, you will have a net negative charge, and these are called anions. An example of this is chloride. So, like I said, you have your nucleus, which is your proteins and neutrons, protons and neutrons, and then you have your electrons, which will be found in electron shields. So these follow very structured rules, these shells. So in your inner shell, so if we take nitrogen, for example, and I go to the periodic table, which I have right here, I see that nitrogen has 7 protons. Okay, so it also has 7 electrons in a neutral state. So in your inner shell can only hold 2 electrons. So there's only 2 parking spots in an inner shell for electrons. So we have our 1, 2. Your inner shell is satisfied, it's happy, it's filled up. So now we move to our next shell, which is shown here as the second outer shell. Your outer shell can hold up to 8 electrons. So then we will go 3, 4, 5, 6, 7, because nitrogen has 7 electrons. Our outer shell right now has 1, 2, 3, 4, 5 electrons, but it has 3 parking spots available. It has a parking spot here, 1, 2, and 3 to satisfy this outer shell. So it has a valence of 3, And essentially this rule is called the octet rule, that an atom wants to satisfy its inner shell by filling it with 2 electrons, and then it wants to satisfy its outer shell by filling it with 8 electrons. A new shell is not added until the previous shell is full. So electrons want to be in pairs. So as you can see here, this one's in a pair, this one's in a pair, this one's in a pair. Those that do not have pairs will be looking for partners. They're looking to make this bond. Like that is how an atom will be happy, is when all those parking spots are filled. So essentially the 4 big elements we think of when we go through our macromolecules are going to be hydrogen, carbon, nitrogen, and oxygen. Okay, and I just kind of want to go through how you would draw this. If we were in class, I would have you guys practice this, and I put a YouTube video here that I want you guys to watch that explains this thoroughly. But here I'm just going to give you one example so that this video doesn't take up a day and a half. And the first thing is I'm going to look for nitrogen on my periodic table. And when we're considering valences in valence electrons, we're going to neglect this whole part of the periodic table. So we're just going to look at these 2, so these 2, and then over here. So we're going to neglect this middle inner part. So we're going to start with nitrogen. So it has this value of 7 up here. So we go to nitrogen, and it's here. So we know that the atomic number is 7. So nitrogen has 7 protons. So we would write 7p positive here because it has 7 protons. Protons are positive. Next we need, in a neutral state, it's going to have 7 electrons. So we would do 1, 2, our inner shell is satisfied. We move on to our outer shell, 3, 4, 5, 6, 7. So it has 7 electrons. However, it has 3 parking spots available, 1, 2, 3 to be completely satisfied. So it has a valence of 3. As you can see, a valence of 5. So it has 5 out here, 1, 2, 3, 4, 5, and it has 3 available parking spots. And then this video will go through so many examples and show you how this is achieved and how this is done, so you will be completely comfortable with the concept when you are done. Let me see, what else do I want to say about this? Okay, so for nitrogen to be satisfied, it'd be much easier for nitrogen to gain 3 electrons and form a bond that could create these three, like form a bond where these electrons can interact, then lose all 5 of its electrons. So it's easier for nitrogen to gain 3, so 1, 2, 3 to satisfy its outer shell than to lose 5 electrons in its outer shell. So I might have wrote this over here. Okay, so atoms form chemical bonds with each other to fill their outer shells. Atoms that have full outer shells will not react with other atoms since they are stable. They're happy, they're satisfied. Only electrons are directly involved in chemical reactions. If their outer shell is not filled, then atoms will either try to gain an electron or lose an electron. So as I said, nitrogen, will it prefer to lose 5 electrons or gain 3 in the outer shell? It will try to gain 3. It takes the path of least resistance. So there are different type of bonds that can be formed between these atoms. We have ionic bonds, hydrogen bonds, and covalent bonds, and we're going to go through all of those in quite some detail. Okay, I think I posted this twice, sorry. Okay, so the first thing is going to be ionic bonds. So here, electrons are transferred permanently between elements and ions are formed. So I'm actually going to go to the next slide, but you guys could come back and refer to this slide as well. Here I have 3 mandatory videos that I would like you to watch that will take this step by step and keep it. And you will be able to see how things are happening, I guess in real time, so it'll be easier to follow along. But here in ionic bonds, we have the transfer of electrons that can bond atoms together. So you have sodium here that only has 1 electron in its outer shell, and you have chloride here that has 7 electrons in its outer shell. So chloride just has to fill that 1 parking spot to be satisfied, and sodium has to fill essentially 7 parking spots or lose 1 parking spot to be satisfied. So when these 2 atoms come in close proximity, or elements come in close proximity, chlorine is going to strip an electron from the sodium atom. And before this happens, both of these atoms are neutral. But once this occurs, sodium now loses an electron and chloride gains an electron. Since electrons are negative, this transfer makes both atoms ions. Atoms or molecules are electrically charged as a result of gaining or losing an electron. So sodium has now lost an electron, so it has more protons than electrons. So it has a positive charge. It is cation. Chloride has now gained an electron, has more electrons than protons, so it is now an anion, and it has a net negative charge. So now these 2 are going to be held together and form a bond because of this opposite attraction, or opposite charge. This is positive, this is negative, so it is going to form an ionic bond. And sodium chloride will now be written like this. Please note that we are not writing sodium with a positive and chloride with a negative, because when they form that bond, they cancel that out. That gets canceled out. So like I said, this video is going to take it step by step, and it's also going to, the third video will show what happens when you have a lot of sodium chloride atoms together. So here we're just showing if one atom collided with another atom and formed this bond. But and actually, this is an example of table salt. I should tell you guys that sodium chloride is a table salt, but as you know, in table salt you have a lot. You don't just have one. So it kind of shows what the structure would look like when you have a lot connecting with each other. So it's pretty neat. So go ahead and watch those 3 videos, please. So then we have covalent bonds. Here, instead of a complete transfer, a covalent bond forms when 2 atoms share 1 or more pairs of electrons. So here you can see that hydrogen has 1 electron and fluoride has 2, 4, 6, 7 electrons. So this would form a nice covalent bond, but they're going to share them. And it's usually depicted by this line. So hydrogen is not going to give up its bond to fluoride. It's just going to share that those electrons. So they are sharing, they are not completely like transferring their electron over. Covalent bonds are extremely strong, and there's a lot of energy that goes into making these bonds. So these bonds store a lot of energy in them. So when these bonds break apart, there's a lot of energy released. So you could have single, double, or triple covalent bonds. So here's an example of double covalent bond. And here we have 2 oxygens and a carbon in the center. And these what do I want to say? These electrons are basically reformatted. So just move this guy over here, then this guy over here, this guy over here, this guy over here. And as you can see, it forms these double bonds. So these are sharing those electrons, and this is depicted by these 2 lines. So this is an example of a double bond. A double bond is stronger than a single bond, but it is not as stable. Same goes for a triple bond. A triple bond is stronger than a single bond, but it is the least stable. And then covalent bonds can, this is just showing how covalent bonds can be drawn in different, so you have the structural formula, the space filling model, and the ball and stick model. And this is actually very important, and it is really difficult for me to just, I guess, speak about it in class. So I put some videos up for you guys to figure out how to make these representations. So I'm going to have you guys walk through those videos. They're YouTube videos, and you'll figure out how you make these ball and stick models. So here's just some more covalent bonds. 1 or more electron pairs are shared between 2 atoms. You can have, like I said, single, double, or triple bonds. You can also have nonpolar bonds and polar bonds. The nonpolar bonds, the electrons are shared equally, and they kind of form this linear representation as shown here. However, with polar bonds, these electrons are not going to be shared equally. So because of the electric negativity value of oxygen, it's going to pull the hydrogen atoms towards it, and it's going to create this kind of like this V shape essentially. So here the electrons are not shared equally. And this kind of takes us to hydrogen bonds. Hydrogen bonds are weak electrical attractions between neighboring water molecules. So as you can see here, you have your oxygen and then your hydrogens. And this is considered a polar bond. By itself, it's not very strong, but in numbers, it is an extremely strong bond. So a molecule of water consists of 2 hydrogen atoms joined to 1 oxygen atom by single covalent bonds. The electrons are not shared equally between the oxygen and hydrogen atoms. So this unequal sharing will create this V shape, which makes it a polar molecule. Because opposites attract, water molecules tend to orient such that hydrogen atom from one water molecule is near the oxygen atom of an adjacent water molecule. So as you can see here, you have the oxygen with the hydrogen, and these are like intermolecular forces, not intra. These weak attractions are called hydrogen bonds. So carbon is essentially the backbone of life, and that is really because carbon can make so many combinations. It has an incredible ability to form very large, complex, and diverse molecules. It is found in proteins, DNA, carbohydrates, as well as other molecules. In addition to carbon, most organic compounds will also contain hydrogen. And here are just some variations of the carbon skeletals you guys can take a look at. So next we're going to move on to activity 2. And here you're going to kind of begin to start building these molecules. So there are 4 classes of macromolecules. You have your large biological molecules. And these classes mainly consist of carbon, hydrogen, oxygen, and nitrogen atoms. Organic molecules are composed of carbon atoms attached to other atoms. So monomers are essentially the building blocks that when they come together in multiples, they will form polymers. So polymers are chains of monomers. Monomers are the individual building block. And all our macromolecules are considered polymers. So our macromolecules are carbs, lipids, proteins, and nucleic acids, and they are all composed of the following monomers. So carbs are made up of monosaccharides. Lipids are actually not true. Fatty acids aren't true monomers of lipids. They're an exception. Proteins are composed of amino acids, nucleic acids of nucleotides. And then there's a video here for you guys to watch. It's a brief introduction to the 4 macromolecules of biology. So all these macromolecules will have functional groups. I just want to see what you guys have to know about functional groups. So many of the important biological molecules consist of carbon and hydrogen atoms. Most of the time, biological molecules have functional groups. Functional groups are groups of atoms that change the characteristics of a molecule. So if you have a hydroxyl group, this OH, added to a molecule, it can now become polar. So I actually prefer your guys' diagram in your book. So hydroxyl, carboxylic acid, and amines are all considered polar molecules. Your hydroxyl group will be more polar than your amine group, and that's because oxygen has a very high electronegativity value, somewhere around 3.5. Your amine also has a pretty high electronegativity value. It's around 3.0, but it's not quite as high as oxygen. Your carboxylic acid, that's actually going to be your most polar functional group just because of the extensive hydrogen bonds it is capable of making. And I actually think of carboxyl as my fatty acid. I don't think about it as my protein. So you are required to memorize these names, structures, as well as where they would be found. And I suggest using the chart in your book or your lab manual versus the one shown above. So your guys' molecules can be written out using a molecular formula or a structural formula. So your molecular formula here is basically just written out with the atoms, which is represented by the letters, and the amount of that atom that is found in that molecule. So here we have 6 carbons, 12 hydrogens, and 6 oxygens found in this particular molecule. And this is the molecular formula for glucose. And then here you have your structural formula, and that's just essentially how this would be orientated relative to one another. And most carbon bonds are shown with lines and not a letter. letter. This is especially true in carbohydrates and starches and things like that. Other atoms are indicated with letters. So you have your structural formula that can be shown like this when you hand draw it. The problem with this is you don't know how they are shown in space in terms of three-dimensional space. So the ball and stick method will allow you to do that. Then you have your space filling model. My favorite would be the ball and stick model because you can see how it is represented in a three-dimensional world. And then there is a distance between your bonds or your carbon and your hydrogen. There's a distance that is needed where the attraction and the repulsion of these atoms is happy. So there's like this certain equation you would have to figure out to determine how long this bond has to be for these two atoms to be completely satisfied. But you guys will not be learning that here. That's further down the road. So if you wanted to build a water molecule, here's a way you could just do it yourself. And it is basically using your wooden skewers to represent the bonds, marshmallows to represent your atoms. You could cut your marshmallows in half for smaller atoms such as hydrogen, and then you could use different colors. Carbon is represented in black, hydrogen in white, and oxygen in red. And so this is how we would build a water molecule. You would obviously need your oxygen, one oxygen atom and two hydrogen atoms, and then you need your bonds, and these are single bonds that you would need. It's a single covalent bond or hydrogen bond. And these videos you're going to watch through these videos, and these videos will talk you through how you determine whether this is going to be a linear relationship. So is hydrogen going to be like essentially just put the toothpick right here and make it linear, or is it polar so it needs to be angled? And you need to look at your electrons in order to make that determination, and the bond size to determine the angle size as well. And these videos will talk you through that activity. So I'll let you guys go ahead and use those videos as your resources, but if you have any questions, just let me know.